All right, this is video 2 of day 1 of 12.5. I'm going to start off because I kind of forgot at the end of the last video. I was going to show you on CalcPlot 3D the very first line that we did. So let's kind of go back up and look at that one. That was the line that we figured out was 1 plus t, 4 plus 3t, and 3 plus 7t. So I went ahead and plugged that into our CalcPlot 3D, and here's your line over here in red. That's the line. And then what I did was I plugged the initial point in that we got just to show you that that actually lies on the line, and that's up here in black. So that's the initial point, 1, 4, 3, that we created the line with. And just to show you that it works, if you plug any value in for t, it should be another point on the line. Well, to make it work so that we could actually put it on here, I actually had to plug in -1/2. So if you plug in -1/2, you get 0.5, 2.5, and -0.5, and you can double check that. But when you plug that in, here is your second point, and they are both on that line. So we did write the equation of the line correctly. Anyway, that's what I wanted to show you. So now we'll come back, and we're going to go ahead and start talking about planes now. And while these are not planes that fly, they are planes in space. So let's go ahead and take a look at what you need. To form a plane, you either need 3 non-collinear points or 1 point and a normal vector. And that's important because you can do a plane either way. So you either need 3 non-collinear points or you need 1 point and a normal vector. So if we're going to go with case number 1, kind of a, I guess, an easier one to think about, because if you have 3 points which are collinear, they might exist in a plane, but you can't really write the equation of the plane. So the easiest thing to do is, well, if I've got some kind of a point, whoops, whoa, what happened there? I've got some kind of a point on the x-axis, I've got a point on the z-axis, and I've got a point on the y-axis. I can very easily create a plane that goes through those points. And obviously that plane right there is only a small triangular piece of the plane, but you would be able to form a plane. The other method, number 2, is if you have 1 point and a normal vector. So let's take a look and see how that one works. So the first thing I'm going to do, I'm just going to sketch a plane down here, or at least do my best to sketch something that kind of resembles a plane anyway, at least part of the plane. Something like that should be okay. So what we've got is I have to know some kind of a point in the plane. Okay, so we're going to call this point right here just some XYZ. So that'll be X, Y, Z. That's just any generic point in the plane. Any generic point in the plane. Okay. I also have to have an initial point. So that's the 1 point here that we're talking about. So I have to have this part. Well, I'm going to put that right here. Doesn't matter where it is, it just has to be someplace in the plane. Well, we're going to call that, because it's our initial point, we're going to call that X naught, Y naught, Z naught. And basically that's our starting point. Well, we said that we needed a normal vector. So the normal vector would be perpendicular, because it's normal, to the plane. What I have is I have some kind of a distance. Let's see, let's go with orange. I have some kind of a distance from 1 point to some generic or any other point in the plane. So what we need to remember is this. I can create a vector between x, y, z, and x naught, y naught, z naught. Okay, we can write that vector. So the vector between those 2 points in the plane is going to be x minus x naught, because it's just the difference between the two, y minus y naught, z minus z naught. And I guess we should probably label that vector right here, this vector that we have right there. Because it's a normal vector, we'll call it n. And for the sake of argument, we're just going to call its components a, b, c, since we don't know them. Again, they're just kind of whatever values those would be. So one thing we should remember is that if we use the dot product of 2 vectors, which are perpendicular to each other, that dot product has to equal 0. Okay, so if I dot the vector that we just created, the x minus x naught, y minus y naught, z minus z naught, with ABC, because those 2 things are perpendicular, that dot product has to equal 0. So let's actually go ahead and perform the dot product. I'm going to multiply the first component times the first component, so I'm going to get a times x minus x naught. Plus, the second component is going to be b times y minus y naught. And then plus c times z minus z naught equals 0. And there it is. That is the equation of the plane. And that shows you that all I need is x naught, y naught, z naught, an initial point, and a normal vector, which is ABC. If I have that, I can write the equation of a plane. Piece of cake. All right, so let's look at a really simple example. Given the point 2, 4, 3 and the normal vector 2i minus 3j plus 5k, write the equation of the plane. Well, according to our formula that we just created on the other page, all I needed was the point that's given. All I needed is the normal vector, so I'm just going to write this in vector form, although you don't have to rewrite it. That's your a, b, and c. So I'm going to write the equation of the plane, which is 2, that's a, x minus 2, that comes from the point, plus, well in this case minus 3, that's from the vector, times y minus 4, that's from the point. And then plus 5 coming from the normal vector times z minus 3 equals 0. That's the equation of the plane. Now we are going to go ahead and simplify this, so we're just going to distribute everything through. So we're going to get 2x minus 4 minus 3y plus 12 plus 5z minus 15 equals 0. We'll keep all the variables on one side, move the constants to the other side, so we get 2x minus 3y plus 5z, and let's see, we get negative 4 plus 12, which is 8, minus 15 is negative 7, but we'll add it to the other side, so we get equals 7. And there's nothing else we can simplify, no common factors, nothing else. That is the equation of our plane. And that's it. Not too hard if they give you the point and the normal vector. But that's all, of course, that's not always going to be the case. Like we said, you could do this with 3 non-collinear points. And of course the question becomes, how do you know if they're collinear? Well, we kind of have to do a little bit of work to figure that out. There are multiple ways to do it, but in this case, let's just go ahead and start by figuring this thing out. So I've got 3 non-collinear points, or at least I assume that they are. That means what we need to do is we need to find vectors between these points. So we're going to call this point A, point B, point C. I want to find the vector between point A and point B, so we'll call it vector AB. So it's important that you know where you're starting from in this case, because it can actually throw things off. So this is going from A to B, which means the vector starts with B minus A. So the vector itself is going to be minus 2, because 0 minus 2, 0, and then 4 minus 0, which is 4. So that's the vector between A and B. So the other key part is, because that vector started at A and went to B, we want to use the other vector as the same starting point. So we're going to use the other vector to be AC, same starting point. Okay, that's important. So AC is going to be, let's see, 3 minus 2 is 1, 3 minus 1 is 2, and 7 minus 0 is 7. So now what I have is I have two vectors where basically the tails are touching. They are, because any two vectors, as long as the tails are touching, are going to lie in the same plane, guaranteed. So now what we can do is we can find the normal vector, because now I have two vectors lying in the same plane. If I cross those, now we're going to be able to figure out a normal vector. And then I can use technically any one of the 3 points and it should work. So now what we need to do is we need to cross those two vectors. If you're really good at this, you can kind of cheat a little bit. I'm going to show you what I mean here. I'm going to throw an I, J, and a K up there. And while it's really not going to be a determinant, you can kind of look at that like a determinant and then just not have to rewrite the whole thing. Probably shouldn't get you guys do it in the habit of doing that, but if you can see it quickly, then you can probably go ahead and do it. We'll go ahead and write it out in this case. So we're going to have our determinant I, it's supposed to be an I, man, this pen just drags. I, J, K, negative 2, 0, 4, 1, 2, 7. All right, so let's see. Eliminating the I row and column, we're going to get 0 minus 8, so minus 8I. Minus for the J, so eliminating the J row and column, we're going to get negative 14 minus 4 is negative 18, so that negative becomes a positive. And then eliminating the K row and column gives us negative 4 minus 0, so minus 4K. So now I have my normal vector. So the normal vector is going to be negative 8, 18, negative 4. And I can use any point that I want to. It doesn't matter. So I'm going to go ahead and just use the first one. I'm going to use 2, 1, 0. So if I use this point, if I use point A, I'm going to get negative 8 x minus 2 plus 18 y minus 1 minus 4 z minus 0 equals 0. And then we'll go ahead and simplify it. So we're going to get a negative 8x, a plus 18y. Let's see what the constants are going to be. Minus 4z. So we're going to get negative 8 times negative 2 is 16. Minus 18 is negative 2. But we'll add that to the other side. So we get a 2 on the other side. This one can be simplified a little bit. Technically, you probably don't want to leave the x negative. It's usually supposed to be positive if possible. So we'll divide everything through by negative 2. So we're going to get 4x minus 9y plus 2z equals negative 1. There is the equation of our plane. Now, I'm going to leave it up to you. You could check it by doing this with B or C, and it should simplify all the way down to exactly the same thing. All right, example 9. Now we want to find a plane through a given point that's parallel to another plane. So now we have to find a plane that's going through a specific point, but it has to be parallel to the plane 5x minus 3y plus z equals 4. Well, the good thing is, and if I don't know if I can sketch this, I'll try. If I've got a plane like this, and then I've got another plane, let's see if I can do this. This is supposed to be parallel to another plane, so maybe you can see that that blue one is like beneath the black one. Maybe the black one is given to us, so we know that the bottom one has to go through our point. So our point 252 has to be in that plane somewhere. Well, the good thing is, if I know the first plane is got a vector of 5, -3, 5, -3, 1, that vector is a perpendicular vector to the black plane. So it's got to be perpendicular to this plane. But if it's perpendicular to that plane and we want the other one to be parallel, it also has to be perpendicular to this plane. So really all that's telling us is we already know our normal vector. The normal vector that we have to use has to be 5, -3, 1. So now we have a vector, we have a point. Plug them in. We're pretty much good to go. So let's see, we're going to get 5 times x minus 2 minus 3 times y minus 5 plus 1 times z minus 2 equals 0. We'll distribute everything, so 5x minus 3y plus z. Let's see what that's going to equal. So we get -10 for a constant, plus 15 is +5, minus 2 is 3, but we have to subtract that to the other side, so we get -3. There is the equation of our plane. All right, got one more piece to go here. Actually, nope, that was it. I apologize. I think that is the last problem. Yep, because we are not doing any of that right there. So we're good. All right, that should be plenty enough.